So now that we know how to draw these different covalently bonded molecules, we can start to describe their actual physical arrangement in three-dimensional space. And that's where we get to our kind of new piece of the puzzle, our valence shell electron pair repulsion, or more commonly referred to as VSEPR diagrams. So what ends up happening is when we've got these atoms starting to come together and form our covalent bonds as they're sharing their electrons between them, we end up with more electrons around them. And as a result, we got negatives here, they end up repelling as far away from each other as possible in three-dimensional space, while still maintaining that bond. As a result, we get very specific geometric shapes that occur in space. And so there's five basic shapes that we're going to get to know this year. There are more, but we're just kind of doing our introductory level at this point. It is linear, don't overthink it, looks like a line. There's bent, where our line bends, don't overthink it. There's trigonal planar, there's trigonal pyramidal, and tetrahedral. There's that tetra again. These are our five shapes that we're going to be able to recognize as we start to draw these molecules in three-dimensional space. I want to show them to you quick. We're going to come back, look at an example when we get to the end, make sure we're feeling okay on how we'd actually identify these. And there's really two things we're looking for when we're trying to identify our shapes. First thing is how many atoms are bonded to the center, and whether or not there's any lone pairs of electrons on the central atom. Are there any pairs, are there any electrons on that middle atom that aren't in a bond? We call those lone pairs. And so by looking at those two pieces of information, we can actually predict with very high fidelity what shape we're going to see in three-dimensional space. So linear, it's just a line. It's straight across, 180 degrees. You can have this when two atoms are bonded together. When you got just two atoms bonded together, looks like a line. Or if you've got three atoms bonded together, so two atoms bonded to the center, and there's no lone pairs, you end up with another flat, straight line molecule, linear molecule. 180 degrees, don't worry about the bond angle on these, just worth kind of talking about. Bent is a little bit different. So if we were to all of a sudden have some lone pairs in here, because we've got this negative field up on top, these atoms in three-dimensional space would bend down and away. And all of a sudden we've got kind of this bent arrangement. The most famous bent molecule is water. If it wasn't bent, we'd be in trouble. Not shown on this model. So we got one oxygen, two hydrogen. What we don't see in three-dimensional space are the two lone pairs. There'd be two sets of dots, two sets of two dots on top, both in front and back. And so that makes these hydrogens repel down and away, making our bent arrangement. Our next shape is trigonal planar. Tri means three. So if there's three atoms bonded to the center and no lone pairs on the middle, it's flat, planar. So three to the center, no lone pairs. We end up with 120 degrees all the way around in terms of three-dimensional space. They're going to get as far away from each other in 3D space. With no lone pairs, they're flat. If you add some lone pairs, it becomes, I guess, pyramidal. Makes this nice little pyramid. And so here we've got two lone pairs, again, not shown on our structure, two lone pairs up here. Because there's this negative field on top, it causes all of these hydrogens to kind of bend down and away. And all of a sudden we've got this nice little triangular prism or pyramid. This is a pyramidal arrangement, trigonal pyramidal. Our last one is tetrahedral, tetra for four. There are four atoms bonded to the center. And more specifically, there's actually four faces. So like if this was a face between these three, there's 1, 2, 3, 4 faces on the molecule, so to speak. That is a tetrahedral molecule, tetra for four. So the question becomes, how do you actually go about identifying this then? Hopefully I want a blank page. Where's my blank page? I don't got one. Gonna need to make one. There's one. Cool. So let's say you had a compound, a covalently bonded compound, that you wanted to actually figure out the geometrical shape. Let me pull up my stuff here real quick. If we wanted to figure out its shape, we would have to start by drawing that molecule. So I'm not connecting. So we'll do this the old-fashioned way. Whiteboard's behind me. Stop share. Boop, boop, boop. So we'd start with our Lewis structures. We'd actually start by drawing it. I'm going to do CO2 because it's a good one to kind of practice a couple different things here. So we always start by counting up our valence electrons. Find carbon on the periodic table. 1, 2, 3, 4 over. It's got 4. Oxygen, 1, 2, 3, 4, 5, 6 valence electrons. We have 2 of them. So +6, +6 for And 6 is 10 plus another 6 is 16 dots to stick our molecule together. We pick a central atom. Step number 2, pick a central atom. We're going to use carbon. When in doubt, use the first one. Carbon's really good at making bonds. Now we're going to join our outer atoms. Remember that each line here represents 2 electrons, one from the oxygen, one from the carbon, one from the carbon, one from the oxygen. If it helps you put the dots on there, we just generally assume that if it's a straight line, covalently bonded, we got 2 dots being shared. We choose 2, 4. So 16 minus 4, we're down to 12 dots. We're going to take these 12 dots, we're going to fill up our outer atoms, because right now as it's drawn, this oxygen only is attached to 2 electrons. So we're going to do 1, 2, 3, 4, 5, 6 more. 1, 2, 3, 4, 5, 6 more. And so now we did 6 and 6. We are out of dots. We need to make sure everybody's stable. Oxygen's got 8, including the bond. We got 8 there. Oxygen's got 8 there. The problem is our carbon only has 4. It needs more dots. And so if we run out, we're going to do some extra sharing. We're going to take 2 dots from this oxygen, bring it up, do a double bond. This oxygen still has 2, 4, 6, 8. Now our carbon has 2, 4, 6. It's closer, still not stable. Wants a full octet. So we'll do it again. Here you go, buddy. I think everybody's got 8 now. Cool. Now the question is, how many atoms bound to the center? We got 1, 2 atoms to the center, 2 atoms to center, to the central atom. And there's no lone pairs. If there's no lone pairs, that means these 2 oxygens, as they get far apart from each other in 3-dimensional space, are going to be straight across from each other. This is going to be a linear molecule. We would say that this is a linear molecular shape, something like this. Only this one would be red. Boop, straight across. Cool. Let's try another one. Let's do NH3. NH3. Steps are the same. Count up your dots. Nitrogen's in the 5th column. It's got 5 valence electrons. Each hydrogen has 1 times 3 is 3 for a total of 8 electrons. As a side note, if you get a odd number here, you're in trouble. Should not have an odd number when you're doing your dot count. Hydrogen, bad central atom. It can only bond once. It only needs 2 and then it's full. So nitrogen in the middle, we're going to do single bonds to attach our hydrogens. Each single bond represents 2 electrons, 1, 2, 3, so 2, 4, and 6. We're down to 2 electrons. Let's fill up our hydrogens. Well, they only need 2. They got 2 with that bond, 2 here, 2 here. Our leftovers go on the center. So now we can ask, how many bonded to the center? We've got 3 bonded to the center. To the central atom. Okay, well, that means it's either going to be trigonal planar or trigonal pyramidal. The only difference is whether or not there's lone pairs, and there are. We've got a lone pair of electron right here on that nitrogen. As a result, all of our hydrogens bend down and away, making this a trigonal pyramidal. This is a trigonal pyramidal molecule. Cool. We're going to be doing a bunch of practice drawing and getting the shapes and looking at our different structures, but hopefully this is a good introduction and overview of how we start to determine what shape based on the number of bonds and whether or not there are lone pairs.